KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.com.
In continuation to the last class, in this class we start with the example 8.3. See here. The magnetic field in a plane electromagnetic wave. The magnetic field in a plane electromagnetic wave is given by By is equal to 2 into 10 to the power of minus 7 Tesla. That is what T sine 0.5 into 10 power 3 sine 0.5 into 10 power 3 x plus 1.5 into 10 to the power of 11 small t. So it is what capital T and it is what small t. This is what magnetic field in a plane electromagnetic wave is given by. The magnetic field in a plane electromagnetic wave is given by, right. Here we have to find two things. One is what is the wavelength and frequency of the wave. What is the wavelength and frequency of the wave. Second one is write an expression for the electric field. Write an expression for the electric field. Okay. See this. Now first what I am asking you is, please try to understand the problem first of all. So what is the problem? The magnetic field in a plane electromagnetic wave is given by. So this is the expression for magnetic field in a plane electromagnetic wave. Regarding this we have to find two things. One is what is the wavelength and frequency of the wave. B is write an expression for the electric field. B is write an expression for the electric field, right, question mark. See here solution A. Comparing the given equation with, this is what given equation, no? Comparing the given equation with By is equal to B naught sine 2 pi into x by lambda plus small t by capital T, right. So if we compare these two, so that we can get it as lambda is equal to 2 pi by 0.5 into 10 power 3. Lambda is equal to 2 pi by 0.5 into 10 power 3. So if you write the values, for example lambda is equal to, for example pi is equal to 3.14, otherwise 22 by 7. By substituting that value here, you are getting lambda value in terms of centimeters as 1.26 centimeters. This is the value in meters. Suppose if you are converting into centimeters, in place of meter we have to write 100 centimeter. With that you are getting 1.26 centimeters, and nu is equal to 1 by t, that is equal to 1.5 into 10 power 11, divided by 2 pi. This is what frequency, right? You know that, no? Frequency is the inverse of time period. Okay. So when you are writing this value 1.5 into 10 power 11 by 2 pi according to the formula, then that will give us 23.9 gigahertz. You know that what is the value of giga? It is what, 10 power 9, no? Right, 23.9 gigahertz. It is what, 1.5 into 10 to the power of 11. This you can write it as 15 into 10 power 10. That you can also write it as 150 into 10 power 9. So 150 by 2 pi means 150 into 7 by 2. That is what 150, right? 150 into 2 into 22 by 7. 2 into 22 by 7. So if we complete this mathematical process, finally the frequency we are getting as 23.9 gigahertz. 23.9 gigahertz. Okay, right. Next, B, that is what write an expression for the electric field. Write an expression for the electric field. See here, B, E naught is equal to B naught into C. E naught is equal to B naught into C. That is equal to 2 into 10 power minus 7 Tesla into 3 into 10 power 8. It is what B naught value. By is equal to B naught into sine 0.5 into 10 power 3 into x plus 1.5 into 10 to the power of 11 small t. That's what here we are comparing, no? So through the comparing you can decide this is the value of B naught. It is not a letter, it is like a unit. Okay, unit, Tesla. See this. So E naught is equal to B naught into C, that is equal to 2 into 10 power minus 7 Tesla into 3 into 10 power 8 meter per second. That is equal to 6 into 10 power 1. 6 into 10 power 1 volt per meter. Volt per meter. Okay, right. Next, the electric field component. The electric field component is perpendicular to the direction of propagation and the direction of magnetic field. The electric field component is perpendicular to the direction of propagation and the direction of magnetic field, right? And this is what we already know that that is from the definition of electromagnetic wave also. So from the definition of electromagnetic wave, so the magnetic field and electric field are oscillating perpendicular to each other, and these two fields are also perpendicular to the direction of propagation of wave. Direction of propagation of wave. Okay, right. So here from that he is also saying once again, but this is according to the solution, not from the statement, not from the definition of electromagnetic wave. Here the electric field component is perpendicular to the direction of propagation and the direction of magnetic field. The electric field component is perpendicular to the direction of propagation and the direction of magnetic field. Therefore, the electric field component along the z-axis is obtained as. If you observe carefully, how we are writing this the expression for electric field component, that is along z-axis, Ez is equal to, see this one, this is same, no? See, whatever is present here, that is same. Sine into 0.5 into 10 power 3 into x plus 1.5 into 10 to the power of 11 t. But here we have written 60. That's how we got this value of 60. See, from this formula, E naught is equal to B naught into C, that is equal to 2 into 10 power minus 7 Tesla into 3 into 10 power 8. So if you complete this process, mathematical calculation, 3 2 is 6, no, and 10 power minus 7 and 10 power 8. Here we are getting 10. So it is 6 into 10 power 1, otherwise 60 volt per meter. 60 volt per meter. Next, example 8.4. Before going to discuss the example 8.4, once you keep in mind what is the information he is expecting to calculate or to do from example 8.3 and what they have given. They have given only one thing, that is what the magnetic field in a plane electromagnetic wave, that is By is equal to 2 into 10 to the power of minus 7 Tesla sine 0.5 into 10 power 3 x plus 1.5 into 10 to the power of 11 small t. From that he is asking to write what is the wavelength and frequency of the wave. Next, write an expression for the electric field. So here we calculated wavelength and frequency. See, wavelength we got it as 1.26 centimeters. So how we got the wavelength? Just by comparing the given equation with the known equation. Next, frequency is inverse of time period, no? So 1.5 into 10 to the power of 11 divided by 2 pi, that is equal to 23.9 gigahertz. Next, B. Here first we calculated E naught value. After knowing the E naught value, you can write the expression for, that is what electric field. But direction is also important because electric field is a vector quantity, no? So the electric field component along the z-axis is obtained as. But while writing the expression for electric field, the electromagnetic picture, the electromagnetic wave picture, the definition of electromagnetic wave also helps for you. Next, example 8.4. Light with an energy flux of 18 watt per centimeter square, 18 watt per centimeter square falls on a non-reflecting surface. I hope you are able to imagine what is meant by non-reflecting surface, right? So whatever the energy is going to incident on that particular surface, it will completely absorb. It will completely absorb. That is what non-reflecting surface. Non-reflecting surface. At the same time, three things will be there. You have to think about these three things. When a light of certain amount of energy is going to fall on one particular surface. So one is reflection, the second is absorption, the third one is refraction. The third one is refraction. But here, light with an energy flux of 18 watt per centimeter square falls on a non-reflecting surface means I am sure that no light is going to reflect. No light is going to reflect into the same media. What is meant by reflection, I need not explain, because in the chapter of ray optics we got it. So as simple as such, bouncing back of light into the same medium, right? Bouncing back of light into the same medium after incidence on a particular surface is simply called as reflection. But here it is what? Non-reflecting. So we have to think that there is no light which is going to reflect back into the same medium. At normal incidence means what is the angle of incidence? Which is 90 degrees now, right? If the surface has an area of 20 centimeter square, find the average force exerted on the surface. Find the average force exerted on the surface during a 30 minutes time span. Okay. So finally, in this problem, what he is asking to find? We have to find, or we have to calculate average force exerted on the surface. To calculate or to determine or to find average force exerted on the surface, what is the given data? Energy flux, that is what? 18 watt per centimeter square, and then area 20 centimeter square, that's you can convert into meter square. Afterwards, the time duration is 30 minutes. Right, see here ma. The total energy falling on the surface is U is equal to 18 watt per centimeter square into 20 centimeter square into 30 into 60. So this is what he is converting into minutes into seconds. So 1 minute is equal to 60 seconds now. 30 minutes means that is equal to 30 into 60. You may have a small doubt here, why he is not converting the unit from, see this is what available in terms of the energy flux is available in terms of 18 watt per centimeter square, and the surface area is also in centimeter square. Obviously centimeter square is the CGS unit now. So generally we may have a doubt why we are not converting the centimeter square into meter square. The reason is, see mathematically these two things are going to cancel now. See here also centimeter square, here also centimeter square, both will get cancelled. So we are saving the time and we are saving the energy while calculating one particular quantity, that is total energy falling on the surface. Okay, right. U is equal to, right, these two will get cancelled, and 30 into 60 into 20 into 18. So this is mathematical multiplication you can do. Finally we are getting 6.48 into 10 to the power of 5. 6.48 into 10 to the power of 5 joules. That is the total energy falling on the surface. Now, total momentum delivered in the bracket for complete absorption. See, while explaining the problem I told you, non-reflecting surface means the total light which is going to incident on the surface will completely absorbed. That he is writing here in the bracket. For complete absorption, total momentum delivered P is equal to U by C. So E value we calculated 6.48 into 10 to the power of 5 joules, and C value we know 3 into 10 to the power of 8. So if you complete this mathematical division, here it is 10 to the power of 5, it is 10 to the power of 8. When this 10 to the power of 8 will goes to the that is what numerator, and here it is 10 to the power of minus 8 will become, and it is what 10 to the power of minus 3 because of this 2, 10 to the power of 5 and 10 to the power of minus 8, and here it is 6.48 divided by 3, that is 2.16. So finally here the total momentum delivered, we got it as 2.16 into 10 to the power of minus 3 kg meter per second. Kg meter per second. Okay. Next, the average force exerted on the surface is, the average force exerted on the surface is F is equal to P by T, that is equal to 2.16 into 10 to the power of minus 3 divided by 0.18 into 10 to the power of 4. Okay. So it is 10 to the power of 4 now. When it comes to the numerator, 10 to the power of minus 4 and it is what 10 to the power of minus 7 will be the factor in numerator, and it is 2.16 by 0.18. Right. Anyhow, what I am saying is, here you do this mathematical division, we are getting average force exerted on the surface is 1.2 into 10 to the power of minus 6. 1.2 into 10 to the power of minus 6 Newton. This is what he is asking to calculate. So, before going to discuss the next problem, once again I am asking you to overlook the problem example 8.4. So, in example 8.4, he has given energy flux and he has given surface area and time, asking to find average force exerted. The formula is F is equal to P by T, but first we have to calculate P, that is equal to U by C, so that we have to calculate U. So after calculating U, you can calculate the total momentum delivered, and after that you can calculate average force exerted on the surface, that is F is equal to 1.2 into 10 to the power of minus 6 newtons. Next, example 8.5. Okay. See here. Calculate the electric and magnetic fields produced by the radiation. Calculate the electric and magnetic fields produced by the radiation coming from a 100-watt bulb. Coming from a 100-watt bulb at a distance of 3 meters. Calculate the electric and magnetic fields produced by the radiation coming from a 100-watt bulb at a distance of 3 meters. Full stop. Assume that the efficiency of the bulb is 2.5%. Assume that the efficiency of the bulb is 2.5% and it is a point source. And it is a point source. Right. See here. So I am asking you to remember the information what they have given in the problem. So what is the information we have to remember? The given quantities, that is what given data, and what we have to find. So in this problem we have to find electric and magnetic fields. We have to find and we have to calculate electric and magnetic fields. What is the information they have given? That is what given data. 100-watt bulb. This is the power of the bulb, and a distance they have given 3 meters, and he is also asking to assume that the efficiency of the bulb is 2.5% and it is a point source. It is a point source. I hope you know what is point source and extended source. Point source means you take that bulb, that is what a tungsten filament bulb, 60 watt and 40 watt, olden days we use 60 watt and 40 watts candle bulbs, that is what point source. And extended source means that is what tube lights. So what we have now, that is what tube light is the example of extended source. Right. Assume that the efficiency of the bulb is 2.5% and it is a point source. See here, the bulb as a point source radiates light in all directions. It is the common phenomena. So we know very well while discussing the theory. So whenever the bulb is going to switch on, right, it emits energy in the form of radiation in all directions. It's a common thing. The bulb as a point source radiates light in all directions uniformly. And he also mentioned the type of the source, that is what point source. Next, at a distance of 3 meters, the surface area of the surrounding sphere is. At a distance of 3 meters, the surface area of the surrounding sphere is. That is A is equal to 4 pi r square. That is equal to 4 pi into 3 square. 4 pi into 3 square. That is equal to 3 square means 9. No? So 9 into 4 and it is what 3.14. It is 22 by 7. 22 by 7. So 4 into 22 by 7 into 9 will give us 113 meter square. This is the surface area of the surrounding sphere. Surface area of the surrounding sphere. Now, The intensity I at this distance is, so this is well known formula, I is equal to power by area, that is equal to 100 watt into 2.5% divided by 113 meter square. 113 meter square, that is equal to 0.022 watt per meter square. This is the intensity I at a distance of 3 meters, right? Next, half of this intensity is provided by the electric field and half by the magnetic field. Here we have to keep in mind what is electromagnetic wave. So electromagnetic wave consists of oscillating electric field and magnetic field oscillating perpendicular to each other and also perpendicular to the direction of propagation of wave. So that's the information we need here to understand the sentence. Half of this intensity is provided by the electric field and half by the magnetic field. That is the reason here they put 1 by 2 I. 1 by 2 I is equal to 1 by 2 epsilon naught E RMS square C. E RMS square C, that is equal to 1 by 2 into, because here we calculated, no, I value we calculated 0.022 watt per meter square. E RMS is equal to square root of 0.022 divided by 8.85 into 10 to the power of minus 12 into 3 into 10 power 8, that is equal to 2.9 volt per meter. This is E RMS, that is what RMS value of E. See this explanation, what he is saying regarding this E RMS. The value of E found above, is the RMS value of the electric field. Okay, that's what, by seeing the notation you can understand what is this. Since the electric field in a light beam is sinusoidal, is a sine wave. Since the electric field in a light beam is sinusoidal, the peak electric field E naught is. The peak electric field E naught is. E naught is equal to root 2 into E RMS. E naught is equal to root 2 into E RMS, that is equal to root 2 into 2.9 volt per meter, that is equal to 4.07. Root 2 is 1.414, no? So 2.9 means like 3. So 3 into 1.414. Otherwise you just take it as 2.9, no problem. Because we don't want any approximate values here. Exact value is also no problem. So that is equal to 4.07 volt per meter is a E naught value. Because that is equal, E naught is equal to root 2 into E RMS. Next. Thus, you see that the electric field strength of the light, that you use for reading, is fairly large. Compare it with the electric field strength of TV or FM waves, right? So communication, see how we are getting TV signal in our house, whether it is Tata Sky or any DTH, whatever it may be, Videocon, but how we are getting. So we are using electromagnetic waves, no? So this is the application of that particular point. See, thus you see that the electric field strength of the light that you use for reading is fairly large. Compare it with electric field strength of either television or FM, frequency modulation, FM waves, which is of the order of a few microvolts per meter. So microvolts means it is indicating that voltage, and meter means it is indicating that distance. Sometimes we are suffering from signal loss and not clear signal. This is all because of that intensity and the distance to what the signal has to travel. The distance to what the signal has to travel. So these 2 points are important when we are getting clear signal. Okay. So in this class we discussed 3 example problems, right? In first example problem, in example 8.3, we calculated wavelength and frequency by knowing the magnetic field in a plane electromagnetic wave. by knowing the magnetic field in a plane electromagnetic wave. Next, this is what B. He is asking to write expression for the electric field. So there we got expression for electric field, that is 60 sine 0.5 into 10 power 3 into x plus 1.5 into 10 to the power of 11 t volt per meter. After completion of that, we went to discuss example 8.4. There he is asking to find average force exerted on the surface. So by using the formula F is equal to P by T, we found the average force, that is what 1.2 into 10 to the power of minus 6 newtons, and here P is equal to U by C and U is equal to this one 6.48 into 10 to the power of 5 joules we got. Next, example 8.5. Calculate the electric and magnetic fields produced by the radiation coming from a 100-watt bulb at a distance of 3 meters. Assume that the efficiency of the bulb is 2.5% and it is a point source, right? So here we calculated, this is what electric field E naught is equal to root 2 into RMS, ERMS root 2 into 2.9 volt per meter. And how we got ERMS means this is what half of this intensity is provided by the electric field and half by the magnetic field. This from the definition of electromagnetic wave, and the intensity we calculated by using the formula I is equal to power by area 0.022 watt per meter square. Right. So at last we can say, you see that the electric field strength of the light that you use for reading is fairly large. Compare it with the electric field strength of TV or FM waves, which is of the order of a few microvolt per meter. Okay, right. Thank you. In our next class, we will continue with the next continuation problem. Thank you.